So in one of the applications in the next section, in section 8.2, we're going to look at if distributions of different categories are the same across different groups. So to give it a specific illustration of that, let's look at the following example. Faculty at universities are typically expected to devote time into three broad categories: teaching, research, and university service. So what we're going to test in this particular made-up example is whether faculty at different institutions distribute their times in similar ways. So there we go. If we let's suppose that we look at the average hours per week spent on each of these categories at 4 different institutions. So we've got 4 different groups, or 4 different populations, if you will. We'll assume that these populations are independent. And we're going to split each of these independent populations into the same number of categories, identical categories, in fact. And they're going to be mutually exclusive and exhaustive, like they were in the previous section. All right. So we've got Millikan faculty say spend 35 hours per week on their teaching, 15 hours per week on research, 10 hours per week on service, and so on down the line. So we want to know, is the proportion of time spent on average per week the same at Millikan for teaching as it is at, say, University of Illinois? Okay, well, it certainly doesn't look at it just from the sheer numbers, but we actually want to do a hypothesis test here to see if that really is in fact the case. And likewise with research, and likewise with service across these 4 institutions. So how are we going to do that? Well, the first thing we have to do is try to come up with an overall estimate for each of the probabilities that we land in a particular category. So let's talk about how we do that. All right, so the first thing we're going to do is we notice that we can total things up here. Overall, if we combine the 4 populations together, overall we see that there's 95 hours spent on teaching. We see that there's 115 hours spent on research and 30 hours spent on service. So we can estimate a probability that any particular observation is a teaching observation, or a research observation, or a service observation, just by taking those fractions. We can do 95 out of 240 is the probability that a particular observation lands in teaching. Doesn't matter across the populations, because again, we're trying to see if they distribute their time in similar ways. So the null hypothesis is going to be that these probabilities down a category are all equal, and then these probabilities would all be equal. So when we're estimating a probability in the first column, we're going to be using the 95 over 240. When we estimate a probability in the second column, we'll use the 115 over 240. When we estimate a probability in the third column, we'll use the 30 over the 240. Okay? And so what we want to do next is actually compute expected values. So to figure out an expected hours per week based on those probabilities, well, we notice that a Millikan faculty member typically spends 60 hours a week working. Okay? And then the probability that what they spend, according to this, if all these probabilities are the same, we're going to estimate that the probability they actually spend, what percentage they spend of that time teaching, is going to be the 95 over 240 using that estimate, and multiply those two together to give it an expected value at n times a p here. So we get 23.75. Likewise, our estimate for what they spend on research is the 115 over 240. And we'll multiply that by the 60 as well, because that's the total number of hours they spend per week. And get 28.75, and then do the same thing for service. So these 23.75, 28.75, and 7.5 are all expected values for what we would expect to see the Millikan distribution of hours spent per week in each of the 3 categories, if these percentages here are good estimates for the common percentages among the 3 categories. We can fill in the rest of the table, and notice that I stopped writing and actually put in an Excel table because, like you probably guessed, we're going to do a lot of stuff in Excel here. These would be your other expected values found in the same way. So for example, notice that the same number of hours per week spent doing anything is 60 for U of I as it was for Millikan. So notice that those expected values in the U of I row are the same. Because again, remember, we're using these probabilities, these percentages, as estimates for the percentages for all across all populations for a particular category. So 90 over 240 is going to be used down this column. 115 out of 240 is going to be used out of this column, and so on down the line. All right, so how do we do this in general to calculate a statistic, and then we'll go back to the specific example. All right, so the second subscript in these are representing which group number is. The first subscript is representing the categories. I know that that's backwards from when you do row and column if you're doing entries in a matrix, but I'm just trying to follow what the book is doing, so that's why I have it backward. I apologize. To me, it feels backward as well. All right, so we have these categories. We have K categories and H groups. Each of the H groups can be divided into K categories. The N1, N2 out to NH are the totals across each of the groups. And we're going to use those again to figure out our expected values. Okay, so again, if P sub ij represents the probability that an observation from group J falls into category I, then we multiply the total in that group times the probability in that particular category. So N sub j times P sub ij, which is what we did in the previous part, right? We took, remember for Millikan it was 60 total, and the probability that we fell into teaching was 95 out of 240. So we took the 60 times the 95 out of 240, which was our P sub ij. Now remember, for a fixed I, the assumption is that P sub ij is the same. So we would use, just like we did in the previous one, here you would use P sub 1, 1, P sub 1, 2, P sub all the way down to 1H down that particular column. All right, so now, just like what we did in the previous section, if these really are the probabilities, then we would expect the expected value to be close to the observation value. And when we add up all of these observations for any particular group, we get that approximate chi-squared distribution if this really is the probability that we're assuming that it is. This is exactly the same reasoning that we used in the previous section. This should be approximately chi-squared of k minus 1 for an individual group, whatever that happens to be. Now again, all of these groups are supposed to be independent, so if I add up these things that are approximately chi-squared over all groups, I still should get a chi-squared distribution, and we add the degrees of freedom. So when we do that, if we sum up over all of the groups and do this double sum, this particular double sum should be approximately chi-squared of h times k minus 1. Now, notice that we, in this particular setup, that we have to have a known P sub ij. Typically, you're not going to know what P sub ij is. Notice that when we did those expected values in the first slide, we actually did a estimate of the probability by doing the total in a category divided by the overall total. Okay, so when we estimate our P sub ij, that's exactly what we do. We sum up over a category. That's what this sum is representing. This is summing down a column. This is sum of the total, the whole thing. This is a P sub ij hat. Now remember, we're assuming that for a given category, the probabilities are all the same. So we need to estimate probabilities across the categories. However, we really don't have to estimate the last category because the last one is 1 minus the previous ones. So we only actually have to estimate k minus 1 of the probabilities because we know the last one if we know the first k minus 1. Okay, so we really only have to make k minus 1 estimates of probabilities. Okay, so then finally, remember, every time we make an estimate for a parameter, this is stuff we talked about in the last section again, every time we make an estimate for a parameter, we lose a degree of freedom. So when we calculate our test statistic now using that double sum that we talked about in the previous slide, we had approximately chi-squared of h times k minus 1, but we have to subtract off, there should be parentheses around that k minus 1 there. We subtract off the k minus 1 degrees of freedom for the k minus 1 estimates that we make, and then we can factor out the k minus 1, and we get chi-squared of h minus 1, k minus 1. All right, so let's go back to the problem at hand. These are just Excel sheets here, or this is just Excel cells where I put in the observed. Over here, I actually used Excel to calculate the expected values. We'll talk about how we're doing that in class, because we're going to spend the class time focusing on how to solve the problem. Okay. Now I want to do, for each of these entries, I want to do observed minus expected squared over expected, just like we did in the previous section. So we do that. We get all of these values over here, these 12 values. We want to sum those things up. When you sum them up, you get 27.82. We want to check that against a critical value. Well, again, we said this is chi-squared on h minus 1 times k minus 1. I've got the wrong chi-squared value here. I apologize. This should be 4 minus 1, because that was the number of categories, times 3 minus 1. That should be the number, 4 minus 1. 4 was the number of groups. 3 minus 1 for the number of categories. So this really should be 3 times 2, which is 6 degrees of freedom, which is going to throw this value off, but it actually makes it smaller, not bigger. You should be able to go into Excel and check what this critical value is based on 6 degrees of freedom rather than 8. So this is not correct. I apologize for that again. I forgot to subtract 1 from my age. All right, so anyway, this critical value is bigger, this test statistic is bigger than the critical value, so we would reject the null hypothesis. Again, the null hypothesis is that the probabilities are the same in a given category no matter what group you're in. Okay, so what that tells us in this particular context is that faculty of these institutions distribute their time in different percentages, which is exactly what we saw from this piece here, right? I mean, this is really what we're seeing. This one's a big discrepancy, or this one here is a big discrepancy, right? So, but we actually did this rigorously with a statistical hypothesis test to, pretty much guarantee that they really do spend their time in different ways. So, like I said, I'll talk a little bit more about this generally during class time, but I really want to spend the class time on how I got these particular cells set up, because once you know how to set the cells up, this is pretty easy to do as you go through each problem. I mean, it's a matter of just being able to do the interpretation. Know that we're going to do the same kind of setup for another scenario as well, but we'll do the similar type of setup. There's actually 2 types of setup in this next section, so we'll do that we'll talk about that as well in class. So anyway, until next time.